Hey guys, so I want to record this too and get it out today. It'll help you with the homework a little bit. And so we're going to do Ampere's law, okay? So that's what we're going to do. We covered it already. I didn't get into it as deep as we're going to do right now. So this might be pretty helpful. Okay, so we have this infinite wire. It's a straight infinite wire. And look how straight it is. And that wire, I'm going to put the current down here, okay? So the wire has some current I flowing through it. And we can draw a loop around that wire, okay? And we can get the B field, okay? Now, if we look at this wire, let's say it's current going into the page, and we do a perfect circle all around, radius r, we can use Biot-Savart law, okay, to get our B field, right? And we've done a perfect circle, so we know that our B field is going to also be a perfect circle about our loop like this. Okay, so we can use Ampere's law, we can use Biot-Savart law, and if we, the fundamental law is the Biot-Savart. Okay, it's always a go-to. You can always get what you need with the Biot-Savart, but Ampere's law helps us so much that we use it, but you can get from Biot-Savart, you can get Ampere's law. Okay, so it's doable. You can do it if you want. All right, so Ampere's law, I'm just going to state what it is. And we've got our B dot dl is equal to mu naught I. What does this even mean? This means we're going to choose a closed loop about some area, and right now, currently, our area has a current enclosed. And since it does have a current enclosed, we'll end up with a magnetic field. If we don't have a current enclosed in our loop, if the current enclosed is 0, or maybe there's two currents and they add up to 0, or whatever. But if this is 0, if it equals 0, we don't have any magnetic field generated, okay? So our magnetic field in that loop that we've drawn would be 0. So this is like a side view here. And then this is edge-on view, or end-on, whatever. Looking at it from the end, okay? Putting your eye right here, and your eyelashes, and your eyeball. Oh, gross. And there's your eyelids. Oh boy. When am I going to stop? Here's your eyelashes. Okay, so you're looking at it with your sick eyeball from the side. Okay, edge on. All right. Okay, so I enclosed is the current enclosed in the closed loop. That's it. And our loop doesn't have to be a perfect circle, okay? It doesn't. So we've got our B field here. Let's draw another loop. I'm going to put R of the B field. All right. But we're going to draw another loop, and we're going to draw our loop like this, okay? And let's give ourselves a section of DL here, and DL, so that's our section of DL. It's going to subtend some angle d theta, and there's some radius r associated with that. So let's look at what we have here. We've got, we really want to get b dot dl, right? So that's fine. That is equal to our magnetic field, which is obviously there's some magnetic field here, okay? There's some magnetic field at every point, okay, along this circle that we've drawn. There's magnetic field. So our magnetic field, whatever that radius is from the center of the current to whatever point. So they're all going to be some different radius. Okay, we'll just call it r. But r and then d theta. Now what about the dot product? What about the dot product? When you do a dot product, you should always get, this is our dl, you should always get the cosine of the angle, right, between the two things, because they're not perfect, right? It's not perfectly in line with each other, but guess what? Guess what? These things are infinitesimals. So in a way, the cosine of theta is always 0. Okay, so cosine, theta is always 0. So the cosine of theta is small, close to 0. So close to 0 that we can say that it's equal to 1. So it's so much equal to 1 that I'm just going to say that we've got a 1 here. And we'll never discuss it again. We're going to give ourselves this 1, and we're going to forget about it in our dot product. Okay, so we've used Biot-Savart, okay? Let's say we used Biot-Savart to get the fact that we know what B is at a certain radius. Okay, so we've used Biot-Savart, and we've got that B is equal to mu naught I over 2 pi r. Okay, so fine. That's good. We can take that knowledge and substitute that in for this guy, and we're going to do, let's keep that. We're going to do our integral. Okay, so here's our integral, the closed loop integral. So we've got our b, but I'm going to instead write b as mu naught I over 2 pi r, whatever it happens to be. And we're going to put our r here, and we're going to do d theta. Well, this r and this r cancel out, so we're left with a closed loop integral of mu naught I over 2 pi d theta. Is there any thetas in here? We don't have any thetas in this bit right here. There's nothing. It's all constant. So we can factor that out. And we're going to end up going in a circle, right, with d theta. Well, what's our circle? It's 0 to 2 pi. So we're going to go 0 to 2 pi. Well, the 0 is going to kick back a nothing, and the 2 pi is going to kick back a 2 pi. So we'll have mu naught I. In fact, I don't like writing it like that. I'm going to do it a better way. We're going to get mu naught I 2 pi from the integral over 2 pi from our B field. And obviously this is going to go away, and we're left with this B dot dl equals mu naught I. And it doesn't matter what our closed loop was, as long as our closed loop contained some enclosed current. Okay? So there you have it. Ampere's law in all of its glory. So let's do this and go like this because it's so useful. It's very useful. All right. So let's see here. What do we got next? What's next? All right. So let's say we have a case of, well, that is not a good circle. Let's get rid of that. Let's see if we can do a better circle. Not quite, but okay, good enough. So here we've got, I don't want to do that either. I always like drawing the current into the page for some reason. So we've got current going into the page, but this whole thing is a solid wire, okay? So the whole thing's a solid wire with total current of I, all right? No, it isn't. I'm not there yet. I'm jumping ahead. Sorry. Let's start over. Well, wow, I am on fire. Come on, guys. So, here's our current. Our B field is going to go around the current at a certain radius. Oh, much better. And what is the direction of the current? Stick your thumb along the end of the page and your fingers point in the direction of the B field. So your fingers should, if you did your right hand, you should see this as your B field. Okay, now we're going to draw our loop like this. Okay? And we're going to pick a couple of sections. So I'm going to pick this section here at some radius. What do I want to call that radius? I guess we're going to just call it R. Okay, I can call it R1. And then another radius out here at R2. But we're going to do the same thing. Okay, so here's our DL. And what I want you to notice is that the B field along the inside part of the loop, and it doesn't matter which way we do, we have to go in a direction on our loop. So it doesn't matter which way we go. We've got our loop going clockwise. Let's do our closed loop clockwise as well. Okay? So in this section, we're going with the current, with the B field, but we're going to come back around and go against the B field in this section here. Okay? So that section we're going against the B field. Over here we're going with the B field. All right? So we're going to do two sets. Here's set 1, here's set 2. And I've got B dot DL. And that's equal to, in set 1, we're going against the B field. So I'm going to put a negative sign. And I've got mu naught I over 2 pi R1. And then I'm going to be doing the same thing we did above, R1 d theta. Okay? So that is what we would integrate. Okay? And now I'm going to do, so that's number 1. Now I'm going to do number 2. And that is BDL equals mu naught I over 2 pi R2 integral. Okay, so awesome. And just so that you can see what it is that we're doing, I'm doing this equation right here. Okay, so I've got those things happening, and all I'm doing is substituting in what B is. Okay, and we already know that B is equal to mu naught I over 2 pi, whatever the radius is at that point. So for number 1, the radius is R1, and for number 2, the radius is R2. So we've got these things, but there's a point exactly halfway. I wouldn't say exactly halfway, but there's going to be additions and subtractions. We're going to do half of our stuff going against the B field, and half of our stuff is going to be going with the B field. And if you notice, the 2 radii cancel out, so we're really left with the complete closed loop integral is going to give us half positive and half negative. So we can then say we've got mu naught I. If you want to divide by 2 pi, you can, whatever. It doesn't matter. But we've got a mu naught I minus another mu naught I, which is going to equal 0. So if there's no current inside your closed loop, you're going to get half positive, half negative, and you're going to end up with 0. So there you have it. That's a pretty nice thing to know. Okay, so all right, so we end up with 0 for anything that doesn't enclose current in the loop. Now, what about direction? Okay, so we could do something where we say, all right, B, if we were to go in a clockwise circle, we would end up with B being positive mu naught I over 2 pi R in the theta hat. So let's just look at our stuff here. So we're going in a clockwise fashion if we were to go clockwise, okay? Now, if we were to go anti-clockwise, counterclockwise, we'd end up with negative mu naught I over 2 pi R. But how hard is this, right? Because what if the current wasn't into the page? What if it was out of the page? Then this one would be negative and this one would be positive. And it's just a mess, right? So what we do is we just ignore all of that, okay? We ignore all of it, and we say that we get our absolute value of B is equal to mu naught I over 2 pi r. And then we look at what we've got. We see which way our current is flowing. We put our thumb along the current and our fingers point in the direction of the B field. And in our situation, put my finger along there and I get a positive theta hat. Okay, we're going clockwise and I'm defining this to be positive theta and this way to be negative theta. Okay, so once I've done that, then you're good, right? You have to define your coordinates and then use the right-hand rule to get yourself the right direction. So when you do all these other integrals, we're doing all this stuff, you're trying to find B, that's fine. Find B. Don't worry about positives or negatives and all that other jazz. Get your B and then figure out which direction it's going with the right-hand rule. Right-hand rule. Okay? All right, so that's exactly what my E&M professor told me, or my class, when we were doing the same biz. Okay. All right. Now, basically, Ampere's law is basically a statement of, does my current, does my closed loop have a current, how do I want to say it, passing through it or running through it. So if your closed loop has a current running through it, then you're going to have a B field come from your closed loop. So let's do an example. I'm going to just draw this crazy closed loop. Nobody cares about this closed loop, but I'm going to do I4 here. Let's put I1 here. Let's do I2, but let's say I2 comes in and goes back out. So here it goes out, here it comes in, and this is I2. Both of those guys, they're connected. But one's going in and one's going out, okay, like a circle or loop or whatever. So that's a looped current, and then we'll have some kind of I3 here. And let's write out what these are. So I1 is equal to 5 amps. I2 is equal to 3 amps. I3 is equal to 4 amps. And I4 is equal to 2.5 amps. So if I were to do my integral, B dot dl, I'm going to get mu naught times the I enclosed. All right, and here's my closed loop. So now, all I have to do is figure out what my closed loop has enclosed as far as current goes. So what do we have for current? We've got I enclosed is equal to I1. So let's say I1. And we're going to add I2, but then we're going to subtract off I2. And we're going to subtract I3. So all of those things add up to give us I enclosed is equal to I1 minus I3. And I1 is 5 amps. I3 is 4 amps. So our enclosed current is 1 amp. Great. I4 doesn't factor in at all because it's not in our closed loop. So it's not there, it's not there. We're not going to get a contribution in our B field from I4. All right. We can now write then our integral B dot dl is equal to mu naught times 1 amp. All right, so good for us. Awesome work. Great job, everyone. Now, let's do a harder situation where we have a circle. I'm sorry, not a circle, a wire, but a wire that is got a center of axis, some radius r. What am I going to name it? R1. All right, and there's a current running through this thing. Okay, I. And we want to know the B field if we draw our loop in a good circle all the way around the center. So we have, I want to put a little r in there. Okay, hopefully you guys can see that. So I've got little r is less than R1, okay? And I want to know what the B field is from just the current going through that part of our wire, all right? So we want to know what the B field is at R. All right, so here's how this works. I'll just write what the question is. What is our B of R at radius R? Okay, so we can write down an equation like we always want to do, and we'll say mu naught over 2 pi r. But we're also going to multiply that by the current, but it's not the whole current. It's a current as a function of r. Okay, so this is actually a really, really good and important equation, because yes, whatever our radius is, that's true. This is going to be our B field, but we can't multiply by the complete I. We have to figure out what our I scales up as. It's not going to be a complete I until it has the complete radius, okay? This is the complete radius of the wire. So we're not going to have that. We're going to be up to that, all right? Or close or inside of it. So the hard part, this is the easy part. This is the hard part. So let's get it. Let's get what that current enclosed is. Okay, do you guys remember J? J is equal to our current density. All right, current density, what does that mean? That is our current divided by the area through which the current is going. So what's the area? The total area is pi R1 squared. Okay, that's our total area. So we have a current density that is equal to I over pi R1 squared. Okay, now what about our current? what about our current for this this IR? What about our IR? So IR, if we rewrite this equation, you can rewrite it as IR is equal to some J. We just figured out what J was, so that's nice. But we've got J times whatever the area is as a function of R. Okay, well, that area is a function of R, AR. That is, let's do this right. AR is equal to pi R squared. So, good for us. We'll say that this is equal to A of R. So we've got J. J is our current divided by pi R1 squared. AR is pi R squared. And the pi's can cancel. And I'm left with IR is equal to I R over R1 squared. R squared over R1 squared. That's good. That's better. Okay. So we're going to go back to this equation. And we're going to say that BR is equal to mu naught IR. So I'm going to put I've got R squared here. And I'm going to put 2 pi R in the bottom and R1 squared there. Well, one of these R's cancels with this R. So that really leaves me with BR is equal to mu naught I times R over 2 pi R1 squared. Believe it or not, that is the right answer. Okay? So, of course, we've got this as our BR. And then you say, okay, well, fine, but which direction is my BR going in? If my current is going this direction, then I put my thumb along the current and my B field then goes like this around. So it would be like that. Okay, so that's the direction of my B field. If I say that this way is positive and this way is negative, then I have a positive B field in the theta hat direction. Okay, so nice. All right, so let's do another one. And this time we're going to have this guy, and we're going to have this guy, and okay, so here's our center axis. I don't like this one. Now I don't like this one. Okay, so our center axis is right down the middle. We've got this R1 here. We've got this R2 here. And basically what we have is some metal with a hole in it. And only current is going through the metal. Okay, so on the inside, all that inside stuff is empty, right? So what do we do? How do we do this? We want to know, we're going to draw a loop. I'm going to draw a blue loop right here. And that's the loop, some distance r. Okay, that's the loop that I want to know what my B field is at that point. Okay, so the question is B of r. All right. Well, it's the same answer as before. B of r is equal to mu naught over 2 pi r times I of r. So again, the hard part is figuring out what I of r is. I just want to make sure I got that right. Yep, okay, good. I thought so. So what is I of r? That's the hard part. Okay. Now, we still have to do the same old thing that we did before. We're going to use J, all right? So J is equal to our I total divided by the area, all right? So now we have to figure out the area, all right, of this section, okay? So the area of, as a function of r, so let's do area of R2 is equal to pi R2 squared. Okay, but that includes this section in the middle, okay? That includes this bit. We don't want to include that bit, so we have to get rid of that bit. So we're going to do R1 as pi R1 squared. And so our total area that we really want, this, let's go back to black. Our area total is equal to pi R2 squared minus pi R1 squared. Cool. We can factor out the pi's, and we're going to end up with pi times R2 squared minus, that is a terrible squared, squared minus R1 squared. Okay, so that is what J is equal to. I over pi R2 squared minus R1 squared. What about our IR? IR. So that equals J times our area of R, right? The area that has current flowing through it. So I'll put area as a function of R. Okay, so area as a function of R, what is that? So we have the same thing. We have area R, and that's equal to pi R squared, but that also includes that green area, which we have to subtract out. So we'll end up with IR equals J. We just figured out what J is. So J is equal to our current over pi R2 squared minus R1 squared. And we're going to multiply that by our area, which is pi times R squared, because that's RR, that's the one that we want, minus R1 squared. So we do that, and I just needed a little bit more room. And of course, this cancels out with that, and we're left with IR is equal to I times R squared minus R1 squared over R2 squared minus R1 squared. Cool. We can now go back to our BR mu naught over 2 pi r IR. And we'll plug that in, and we get our BR is equal to mu naught I over 2 pi r. And then we're just going to multiply by our R squared minus R1 squared over R2 squared minus R1 squared. And that is our answer for that case. All right. This is really important for homework 9, problem 6. Okay, so homework 09, problem 6. Essentially, this will get you the right answer. Okay, so there we have it. I just wanted to clear that up before we start talking about solid state magnetic properties tomorrow. All right, good luck, everyone.